Hello everyone, I am Juliete Rossie and I am pleased to present our work on behalf of my colleagues Berken, Utku, Demirel, Adnan, Harun, Dogan, Max, Möbus, and Christian Holz. I would like to present our paper introducing a novel continuous cybersickness detection technique using EEG-based multitaper spectrum estimation. A significant drawback of VR experiences is that many users continue to experience discomfort during and after exposure. This condition, known as cybersickness, manifests through symptoms such as nausea and dizziness, affecting user comfort and limiting widespread adoption. As VR applications continue to develop, there is an increasing need of effective methods to detect, monitor, and prevent cybersickness. Existing detection methods fall into three main categories: stereo image-based detection, physiological signal-based detection, and motion-based detection. Each has some strengths but also many notable limitations: limited generalizability, the use of pre-recorded videos, requiring seated conditions with restricted locomotion, and the use of subjective questionnaires providing discrete data, making real-time interventions difficult. To address this limitation, we propose a continuous cybersickness detection method based on electroencephalography, or EEG, and head motion signals. We recruited 16 participants, 6 female and 10 male, for our experiment, aged between 26 and 37 years. Participants were strategically positioned within the VR environment based on their height and arm length to ensure accurate interaction. Each participant completed the experiment across 2 sessions. In each session, participants were exposed to the same VR task, and cybersickness was monitored continuously. The experiment took place in a realistic cycling simulation designed in Unity 3D, enabling free head movements. This environment was selected to provide a highly immersive experience to trigger and observe cybersickness symptoms. The EEG signals were recorded using the DSI-24 dry electrode system synchronized with the Oculus Quest 2 headset. The EEG system was used to detect neural patterns associated with cybersickness, while the Oculus Quest 2 provided the immersive VR experience. Real-time cybersickness levels were recorded continuously via a joystick, enabling participants to indicate their discomfort during the experiment. At the end of each session, participants also completed the Simulator Sickness Questionnaire, or SSQ, to provide subjective feedback on their experiences. From the collected data, we explored individual variation in cybersickness. The participants' cybersickness level differs significantly between one another. The maximum level ranges from 0.1 to 0.8, while the standard deviation reaches 0.4, proving that the VR immersion is dynamic and subjective, which justifies why it is not optimal to predict cybersickness using the VR frames. We also conducted an analysis of cybersickness reporting correlations between real-time and SSQ. We computed the correlations between users' joystick responses in VR and their SSQs that were conducted at the end, mainly for the nausea, oculomotor discomfort, and disorientation symptoms. The microcorrelation is the correlation between each experiment conducted amongst 13 users, and the macrocorrelation is a user-wise correlation. There is a significant correlation between the user's joystick response and their overall feeling of sickness, meaning that they engaged with the joystick more frequently or intensely the more the score of SSQ was high, showing a direct link between the verbal reports and the behavioral measures. For the data processing, we conducted a straightforward filtering on the EEG data, starting with its segmentation into 3-second windows without overlap before pre-processing it. To reduce noise artifacts, the signals were resampled from 300 Hz to 100 Hz. We applied a bandpass filter between 1 and 40 Hz to retain only the neural activity. Finally, a notch filter at 50 Hz to remove power line interference. The multitaper method is used for spectral estimation because it reduces temporal variability and minimizes non-stationary noise in EEG signals, outperforming standard periodogram techniques. However, cybersickness is inherently non-stationary, with symptoms that can change abruptly, making long analysis windows impractical. To address this, we propose computing the power spectral density, or PSD, within 3-second windows. Instead of relying on absolute PSD values, we introduced the temporal relative PSD, or TR-PSD, which measures changes in spectral content over time. This is computed as the difference between the PSD in the current window and the average PSD of the initial 3 segments, allowing for more responsive cybersickness detection. From the kinematic data, we extract features without any filtering. We extract the difference between 2 consecutive segments of the head position and head rotation, i.e. X, Y, and Z, and roll, pitch, and yaw. We compute the Euclidean norm of the head position and the head rotation, and finally we compute the first difference of the head speed and rotation. The 1/f spectral slope describes the changes of frequency in the power band of 30 Hz to 45 Hz, assessed via the slope of a regression line fitted to the PSD on a log-log scale from 30 to 45 Hz. We found for the first time a link between 1/f and cybersickness. In the figure, the 1/f is the red line, the sickness level is the blue line, and the gray line is the inertial measurements. The sickness level shows a strong correlation with the 1/f features, demonstrating that EEG provides a valuable insight into understanding cybersickness compared to inertial measurements, even though they remain commonly used. We propose an architecture for estimating cybersickness that is composed of 2 encoders, one for the EEG data and one for the kinematic data. Each encoder is composed of a convolutional layer of 16 kernels of size 2 and an LSTM cell with a hidden size of 32, after which we apply batch normalization. Then the concatenated data from the 2 encoders are passed through 3 fully connected layers with sizes 10, 20, and 40. Our results show substantial performance improvement from our method, reaching up to 10 to 15%. The method solely based on kinematic features failed to detect cybersickness levels. We also show that the pre-processing step with the modified multitaper TR-PSD significantly improves the performance and increasing it to up to 20%. Additionally, employing our TR-PSD leads to an increase of performance of 12% compared to straightforward multitaper. Conversely, incorporating the kinematic information only increased the results by 5 or 6%. Moreover, adding kinematic features with the raw EEG decreases the performance, implying introduction of noise or redundancy. To conclude, we introduced a novel multitaper-based EEG processing technique for cybersickness detection. A dataset with 16 participants with real-time EEG and motion data publicly available demonstrated real-time continuous cybersickness estimation with high accuracy. For future work, a larger and more diverse participants group is needed. Additionally, future studies should evaluate performances across different EEG devices. And finally, testing in various VR scenarios can improve robustness. We hope our contributions will advance cybersickness research and improve VR user experiences.